So I'm going to record this because this is kind of a new thing to you guys. I want to make sure that we have it available and have it up so you can go back and look at it. There's some things here that are kind of tricky, and anyway, I think you'll like it. And Quinn's here, so he'll want to be able to have these things. We've been missing you. Welcome. You're now permanently saved in the recording. So you can go back and listen to that anytime you like. Say, hey, that was me.
Go back and watch this recording.
So the nice thing about math is that the objectives, the thing you're supposed to learn, is almost always the title of the section. This is about the derivative shortcuts. Guess what we're supposed to learn? We're supposed to be able to take a derivative using the shortcut. So when we're done, think about this. Can I take a derivative using the shortcuts? The nice thing is they are, in fact, way shortcuts. Some shortcuts don't cut off a whole bunch. This cuts off a whole bunch and simplifies a whole bunch of things. Now, this already should be in your notes someplace. The limit of the difference quotient. This is where we started the whole conversation of derivative and how it worked. And the premise, let me remind you of this real fast, was I would have some kind of a curve. And this curve, I would be interested in the tangent line at a particular point. So the tangent line at that point might look like that. And the idea is the slope of that red line and the slope of the black line at that point are the same. But if I wanted to find what that slope is, the problem is, in order to find slope, you need 2 points. And so what I would do is find another point. And so I would call this one x, and this point over here I would call x, but I would have to add something to it, right? And get x plus h. And that's where this comes from. Look, this is the this point up here is the point f of or x and f of x plus h and f of x plus h. So you've got those 2 points, and that's where this comes from in the numerator. F of x plus h minus f of x. That's the difference in the y values between this point and this point down here, which is x and f of x. And so what happened was, remember the idea was I would make this guy get a little closer, and so what would happen to this line was the slope would get a little closer. See how the slope gets closer as I move that point over? And the more I move this point over, the closer the blue line slope and the red line slope get to each other. There it is. That was the whole idea. The smaller and smaller and smaller h gets, the closer I get to the actual slope. Now you remember the whole process. We'd plug all this stuff into here, and eventually a whole bunch of things would cancel out, and what I would be left with would be only h's, stuff with h's in the numerator. And then I was actually able to make the h in the denominator cancel out, and then I could actually plug 0 in for h. Yay! La! Okay, that was a long process. But that was a 30-second reminder about what we did in the previous sections, about why we were doing the limit of the difference quotient. It's to find the slope of this line. But now we also used that when I had, for example, if I had a shape that was a parabola, I could find out where that point occurred. Remember, the slope of the tangent line there was equal to 0. And so I could find out where the maximum occurred. So there was a lot of reasons. And right now, there's a lot of calculus beyond the reasons why the derivative is a huge, huge deal. If you're thinking about majoring in finance or business, or you will spend a ton of time dealing with derivatives, it comes up a lot. And so there are a lot of applications for derivatives. Right now, we're just kind of sticking to some real basic ones. So how do we do this without having to run through all those major steps? Here's a first shortcut. Get this one down. If you have a power function, x raised to a power, the shortcut is, as it turns out, and perhaps you've seen this, and some of you were beginning to pick this up already, I think, because we did a lot of derivatives that had an x squared in it, and x squared always ended up having a 2x in the answer. Well, the reason is, this is what happens. When you have a power, the power just simply multiplies down front, and then the power gets smaller by 1. So, if I had x to the 4th power, the power multiplies down front, and then the power gets smaller by 1. That simple. Now you could do that with the limit of the difference quotient. You'll get the same answer every single time. So the nice thing, it's like a little kid made this up. You know, you ever go out and you're playing and you just kind of like make up the rules? No, you're not allowed to go in the backyard. Backyard's out of bounds. I don't know who made that up. They just did. That was one of the rules we always had. So anyway, my point is, though, it looks like it's just a goofy little thing, but a lot of research has been done to figure out that this is the pattern. This is what happens every single time. If you have a number multiplied out front already, some coefficient out in front, and it's just a multiplication right here, then, well, as it turns out, that coefficient just stays there, and you do the exact same thing. The n comes down, the exponent, and then the exponent gets smaller by 1. So 3x to the 5th power would simplify. The 3 just kind of stays there, and then the 5 comes down front, and the exponent gets smaller by 1. Every single time, that's the pattern. And now, in this case, then, the 3 and the 5 multiply and get you 15. Let me take a deep breath there. Questions? Alrighty, onward. If I have a couple of things added together, you can just treat them individually. So look what happens. If I have a polynomial here, you just take the derivative of the first one plus the derivative of the second one. Just treat the terms as their own little individual problem. And by the way, that also works with subtraction. If this was f of x minus, it would just be the subtraction down here.
How is that different? How does that change?
I'm not sure if I understand what you mean.
So
here this was just one term. This is one term, nothing being added or subtracted. So what if I had two things being added or subtracted? Well, you just take the derivative of each of them individually. Now, as it turns out, if I have two things multiplied, if this was a multiplication problem here instead, something times something, now it turns out it's a totally different process. And there's a totally different rule that we're not going to get into. But if you got some things added together, you just simply, you just simply take the derivative of each of them individually. So, for example, if I got 2x to the third minus 4x squared, you just take the derivative of the first one, just like we did a minute ago, minus the derivative of the second one. So the exponent multiplies down, becomes a 6. Exponent gets smaller by 1. Exponent multiplies down, becomes an 8. Exponent gets smaller by 1. X to the first power. Okay? There's actually one here that's missing. Let me insert one here. What if I have y equals 3x? Take the derivative. So y prime equals, well, the exponent is currently a 1. So you multiply the exponent down. 3 times 1 is 3, times x raised to, then the exponent gets smaller by 1 and becomes x to the 0. And x to the 0 is equal to 1. So you end up with just 3. Okay, gentlemen?
I'm all right.
Good. All right. So now think about this for a second. What is this? What is this shape? If you graph that, what is that? Be more specific. What kind of line? A straight line, not horizontal, not vertical. Kind of. Tell me something about what's the 3 doing to it? It's the slope. Do we remember y equals mx plus b? In y equals mx plus b, the number in front of the x is the slope of the line. What's the slope of this line? What's the derivative? Say this 5 times in your head. The derivative is the slope The derivative is the slope. The derivative is the slope. The derivative is, what's the derivative? Nice job. That's called learning. See, if I'd come up to you 3 minutes ago and I'd say, hey, what's the derivative? You would have gone, because you were absent a couple of days, right? And now that you're back, you've learned. So happy. The derivative is the slope. And so when you've got a straight line right here, when you got this straight line, you should be, without even thinking about it in terms of calculus, you should be able to look at that equation and say, what's the slope of that line? 3. And now, by the way, the slope of that line is 3 everywhere, right? It doesn't change. It's always 3. As compared to when I do y equals, nope, not that one. When I do y equals x squared, the slope of that one is 2x. And notice how 2x has a variable in it. Because the slope varies, right? Depending upon where you're looking. But in this guy, the slope is 3 always. There's no variable in the derivative. All right, onward. What if you have a constant? F of x equals, for example, 5. What kind of shape is that if I graphed that? It's a straight line. What kind of a straight line? Horizontal, not vertical, horizontal. Y is 5, negative 3, 5, 2, 5, 8, 5, 0, 5. Horizontal line. What's the slope of that horizontal line? 0. And so the derivative of a constant, is always 0. Because it's a horizontal line, regardless of where it is. So if this was x equals 4, the slope of that line is 0. If it was x equals 14, all that would do is move this line up farther, right? Still, the slope is 0. If it was negative 14, that would just simply bring it down real far. But the slope is still 0. So regardless of what number it is, the derivative of a constant is 0. All right. So let's see if we did have learning. Put our toys away and take a derivative using everything you just learned. So that's what you should have. Let me run through the steps. First of all, it's the sum or difference of a bunch of things. So in the problem, Corbin, that you were asking about, what I've got here is just think of it as a whole bunch of individual little terms that I can deal with. So first one, the 5 times the 4 gets me 20. That's what comes out front. The 5 gets smaller by 1. I take the 2 times the 7. That's negative 14. Comes down front. The 2 gets smaller by 1, becomes 1. 2x to the first power, the 1. 1 times 2 is the 2. And then the exponent gets smaller by 1. So I would have x to the 0 power, but x to the 0 power is just 1. And then the derivative of a constant, 0. So you don't put 9 on there. Derivative of a constant is 0. Do another one. We're just going to do a few of these right in a row. Equation, but it's not in the derivative. So the derivative here would be that. Now, here I used the notation y. So a lot of times we'll use y prime. It means the same thing as f prime of x. Just depends on how you want to write the notation. Both of those mean the same thing. Agree? Question? Cameron, what you got?
I messed up on the whole middle section.
All right, so let me run through the logic. The exponent multiplies down front. 2 times 3 gets you 6. Exponent smaller by 1. Exponent multiplies down front. 3 times 2, 6. Exponent smaller by 1. There's a 1 right here. 1 times 36, negative 36. Exponent smaller by 1, that makes it x to the 0 power, which goes away. And the derivative of a constant is 0. One more. Get the hang of this. Yes? New question. Now, find the maximum values. Same equation, right? So let's go through a little bit of thinking here. Let me remind you about what that kind of a shape looks like. Way back first, second quarter sometime, we spent a lot of time graphing these kinds of things. And we're supposed to know off the top of our heads that cubics look like that. Now, up to this point, if I remember on the quiz yesterday, when we did a max-min, you had to do the limit of the difference quotient. That would be a little bit of a pain to do the limit of the difference quotient on this. I'd have to plug x plus h into that and cube it, and then plug x plus h into there, and then square it, and then plug x plus h into there, and distribute the -9, and then I'd have to subtract f of x. Put that all over h, and of course, every single time I write one of those lines, I'd have to write the limit as h approaches 0 in front of those. Kind of a pain, but it's part of the notation. And that would be a long process. It would take a good 5 minutes to get through that problem. But what do we notice about this graph? Look at the question, max mins, right? There's a max and there's a min. And what do we know for sure at those 2 points? Slope is 0. No matter what's going on anywhere else, at those 2 points, I know the slope is 0. Listen to that sentence she just said, because she gave us the answer. Slope is 0. So how do I find those points? No. Set it equal to 0. Good idea. But plugging in 0 would have found you the slope at that point right there, where the x value is 0. See what I'm saying?
Yeah.
But what I want to know is, I want to know where the slope is 0. So we're not plugging 0 in. That would tell me what the slope at 0 was. I want to know, see, the difference is I know the answer. I know the answer to the slope equation is 0 at those 2 points. I want to know where that happens. So I take the derivative and I set it equal to 0. Now remember first quarter? Somewhere back in the first quarter, I think I mentioned once or twice about factoring. That it was kind of a big deal that you had to know how to factor. You, of course, would solve that equation by, let's say the word factoring. Yeah. And so I noticed that there's a 3 in all 3 terms. And then I glance at the second term and I notice, aha, it factors. And so you would, on your paper, of course, factor that. And you would find that the factors of that are ding, ding, ding. And then, of course, you have my favorite property. Except the property on which I live. I like that property. No. Zero product property. If you got a bunch of stuff all multiplied together and the answer is 0, somebody has got to be 0. Could it be the 3 that's equal to 0? No. But it could be the x minus 3 and the x plus 1. And if that were the case, if x minus 3 were equal to 0, that would mean x would be 3. And if x plus 1 was equal to 0, that would mean x equals -1. So what that tells me is that these 2 points, these mystery points, are -1 and 3. Now listen to this scenario. I'm a manufacturer of aluminum cans. And I have discovered that when I produce and sell 10,000 cans, that's when I will maximize my profits. Now, profits, of course, are based upon the revenue you bring in, but also minus the cost of what it takes to produce the thing, right? You have labor costs and material costs and shipping costs, and there's a lot of costs involved in the actual production of something. The revenue is what you sell them for, and the difference in those two things is your profit. So I've discovered that if I sell 10,000 cans, I will maximize my profit. So does that mean I put $10,000 into the bank? Not necessarily. It depends upon how much profit I actually make on each can. So let's say these were some super duper really special kind of can, and I sell them for $5 a piece. If I sell them for $5 a piece, no, not sell them for, but I make a profit of $5 a piece, which probably means I sell them for $7 and have $2 in costs, but I profit $5 a can. I don't know, something special about these cans. So, but I earn profit of $5 a can. Well, if I sell 10,000 cans and I make $5 a can, 5 times 10,000 is $50,000. That's the profit that ends up in the bank. There's a difference between where the maximum occurs and what the maximum is. If a different company, for whatever reason, has the same production kinds of realities, they're going to maximize their profit at 10,000, but they're only making a profit of $2 a can. They're only going to make $20,000, whereas my company made $50,000 somehow. So there's a difference between where the maximum occurs and what the maximum is. Look at these two graphs, the black one and the green one. They both have a maximum down here at this A value. But what the maximum value is different depending upon how high it is. So the height of the graph is the question that this is asking for. What's the maximum and minimum value? Not where does it occur. That's important. It occurs at these points down here. But what is the actual maximum or minimum? And so what do I need to do to find those numbers? Those are Y values. And of course, this entire test quiz would be a without calculator quiz, because all of this can be done in the calculator. I want to see if your brain works. So, another fun fact you should remember about cubics. The basic shape, right? The up, the down, the back up. As backwards as it seems, look where the maximum occurs. The maximum occurs at the smaller number. It occurs at the number to the left. And the minimum value occurs at the number to the right. So if I told you this was a cubic and these were where the extreme values occur, you should look at that and say, oh, the maximum is going to occur at -1 and the minimum is going to occur at +3. Seems backwards, I know. Putting the smaller number in actually gets you a bigger answer. So this is what you need to be able to do. You need to find the Y value at each of those points. So I'm going to plug the Y value into each of these two equations, do the computation, and see what I get. Yes, you need to be able to do this by hand with your own little brain. Yeah? And actually, it's really not that hard, because you have a superior brain if it would just be put to use. Sometimes you might have to take your socks off even. All right, so just to kind of prove the point and check some things here, we're going to graph this on the calculator. So dig out your machine, graph that original equation, and look at the Y value here. So find a window that's going to let you see the top and the bottom of this graph. So here's the windows I came up with and the graph I came up with. and I did a calculate, went second calculate above the trace button. I calculated a value at -1. Sure enough, it came out to be +1. Did a calculate a value at 3, and sure enough, it came out to -30, or yeah, -31. So I'm verified on the calculator what the calculus proved to me. I would agree with you. Put the right graph in. X cubed minus 3x squared. You got a -3x squared, which is different than -3x squared. That's it. That's the logic of this. Here's homework problems. These are the kinds of questions you should be at. Now, what I didn't talk about in the notes was this kind of a question. This one says, find the equation of the tangent line. What do you need to know to find the equation of the tangent line? Point and a slope. What's the derivative, Quinn? The derivative is the slope. And so if I want to find the slope, I need to take the derivative of that. And then, in this case, substitute in 1. Because I need to know what the slope is at 1. And then, I also need to know what point, so you're going to need to figure out what the y value is at that point. So that's it.